Hello, everyone. Recently, scientists have rekindled their curiosity about whether we are truly alone in the universe. This renewed interest was sparked by thousands of messages coming from a single source in space. Have they decoded these messages? In today's video, we will explore the details of scientists detecting a massive object sending us thousands of signals. Let's dive in. For many, fast radio bursts (FRBs) might not mean much, but for astronomers, scientists, and space enthusiasts, they are fascinating. The allure partly comes from their mysterious nature, as not everything about them has been discovered yet. Imagine the excitement of scientists when they start receiving countless radio signals continuously. The vastness of space is filled with enigmas, and solving them might take forever. FRBs are one such mystery. Receiving these signals might suggest that someone is trying to communicate with us. But should we respond to these calls? FRBs are intense bursts of radio emissions lasting milliseconds and exhibiting unique dispersion of radio frequencies. The first FRB was discovered in 2007 by Duncan Lorimer, but scientists found records of FRBs in the Large Magellanic Cloud Survey 6 years before this discovery. When a telescope detects an FRB, researchers focus on its dispersion, the measure of how much the radio burst slows as it reaches Earth. Plasma between stars and galaxies causes all radio waves to slow, but lower frequencies experience a more significant slowdown than higher ones. An FRB contains various frequencies, with higher frequency light reaching Earth before the lower frequencies. Scientists use this dispersion to determine how far the FRB source is from Earth. The broader the burst, the more plasma it has traveled through, indicating a distant origin. Scientists recently discovered intriguing phenomena around Sagittarius A, the supermassive black hole at our galaxy's center. Astronomers found a new class of objects near this black hole. These objects usually appear dense, but stretch as they orbit close to the black hole, a process that can take over 1,000 years. In 2005, scientists identified an object named G1 near the galaxy's center. In 2012, they found a second object, G2. By 2014, G2 was observed near the black hole. Initially, G2 was thought to be two stars orbiting the black hole, merging into a single massive star, hidden by a thick cloud of gas and dust. More recently, scientists discovered for more objects G3, G4, G5, and G6 each with different orbits. Researchers believe these 6 objects were originally binary stars, forced to merge by Sagittarius A's strong gravity. This merging of stars suggests an increase in stellar mergers in the universe, possibly making most stars observed today the end products of such mergers. The interaction between black holes and galaxies is perplexing, prompting increased efforts to understand it. Despite their similarities, G2 stands out because it hasn't stretched as much as the others. Scientists believe something inside G2 keeps it dense and intact despite the black hole's influence. These G objects likely feed the insatiable Sagittarius by providing gas, demonstrating that not only in the Milky Way, but also in other galaxies, things are chaotic. Until now, scientists have only mapped exoplanets that might support life, without finding signs of intelligent life. However, everything changed when they detected a space signal from Proxima Centauri, the closest star to our solar system, sparking new hope for life beyond Earth. Proxima Centauri is fascinating because it's the nearest star system to us, only 4 light years away. Discovered in 1915 by Robert Innes, Proxima Centauri is part of the Centaurus constellation and can only be observed with a telescope. It hosts exoplanets, making it a point of interest for astronomers. Proxima Centauri, a red dwarf star, is much smaller and less massive than our Sun, but is 33 times denser. Despite its low brightness, it randomly emits intense solar flares filled with high radiation. These flares impact its orbiting exoplanets, Proxima Centauri B and C. There's also a potential third exoplanet candidate, Proxima Centauri D, which takes about 5.2 years to orbit the star. Proxima Centauri B, about 1.17 times Earth's mass, orbits the star at 7.5 million kilometers and completes its orbit in just 11 Earth days. Being in the habitable zone, This exoplanet could have an atmosphere and surface temperatures conducive to liquid water, suggesting potential habitability. However, the star's frequent, intense solar flares raise doubts about its ability to support life. Scientists debate whether Proxima Centauri b could host life due to its high radiation levels, which could lead to increased oxygen and carbon monoxide levels, facilitating the evolution of complex chemicals and organisms. Some scientists even speculate that the recent signal from this region could indicate the presence of extraterrestrial life. Recently, scientists detected a signal from Proxima Centauri, significantly boosting the possibility of extraterrestrial life. In April 2019, a radio signal believed to be from Proxima Centauri was detected. This signal, named Breakthrough Listen Candidate 1BLC1, was discovered by the Breakthrough Listen Project, a $100 million initiative to search for intelligent extraterrestrial communication using advanced telescopes. Detected by the CSIRO Parkes Radio Telescope in New South Wales, Australia, the signal stood out among millions of others due to its narrow bandwidth and Doppler shift, indicating it was from a distant source rather than Earth. Initially, scientists did not notice BLC1 as they had to sift through millions of signals, eliminating those of terrestrial origin. After careful analysis, scientists identified BLC1 as a unique techno signature. The signal, unlike the famous WOW signal from 1977, which lasted 72 seconds and was never detected again, showed a consistent pattern over 30 hours. While the WOW signal remains the best evidence of an extraterrestrial radio broadcast, BLC1's consistent presence prompted further investigation. To confirm BLC1's extraterrestrial origin, scientists replicated the initial observation conditions 2 years later, but found no similar signals from Proxima Centauri. They explored various possibilities, including moving transmitters, satellites, and deep space probes like Voyager 1 and 2, but none matched the signal's characteristics. Space remains filled with mysteries, and the search for extraterrestrial life is ongoing. While we've made significant strides, the universe continues to surprise us with its enigmatic signals. Stay tuned for more updates on this fascinating journey. Don't forget to like, share, and subscribe. Until next time, keep looking up at the stars.